Hello, mathematicians. Let's talk about valid and invalid arguments. When I say an argument, I don't mean a fight. An argument is a carefully constructed uh, sequence of statements that allow you to draw a logical conclusion. Now, all statements in an argument um, are called premises or assumptions or hypotheses. The final statement, the conclusion, of course, is called a conclusion. Now we have a symbol that we use, these three triangles. You'll see these three dots that form a triangle. And we read that therefore, and it is normally placed just before the conclusion. To say that an argument form is valid means that no matter what particular statements are substituted for the statement variables in its premises, if the resulting premises are all true, then the conclusion can be drawn. To say that an argument is valid means that its form is valid, okay, without regards to what the particular statements are, simply that the form of the argument is a valid form. Okay, so how do we test an argument form for validity? First, we must identify the premises and the conclusion of the argument form. We'll construct a truth table showing the truth values of all the premises and the conclusion. A row of the truth table in which all the premises are true is called a critical row. If there is a critical row in which the conclusion is false, then it's possible for an argument of the given form to have true premises and a false conclusion. So the argument form is invalid. If the conclusion in every critical row is true, then the argument form is valid. Determine whether the following argument form is valid or invalid by drawing a truth table. Indicate which columns represent the premises and which represent the conclusion, and annotating the table with a sentence of explanation. When you fill in the table, you only need to indicate the truth values for the conclusion in the rows where all the premises are true, the critical rows, because the truth values of the conclusion in the other rows are irrelevant to the validity or invalidity of the argument. So this is an example of an argument form where P, Q, and R represent some unknown statements. So we have two premises. P implies Q or not R. Q implies P and R. And the conclusion is that P implies R. And so we'll use a truth table to determine if this is a valid argument form. So since we have three statements, P, Q, and R, we begin with our 8 rows of all the possible combinations of truth values of P, Q, and R, starting with the possibility that P, Q, and R are all true, and then all the variations leading to the fact that it's possible they could all be false. So notice we have our premises and we build up to the premises. We begin with a column to negate R. And remember, when you negate one column, you're simply toggling all of the truth values. If R is true, then not R is false. If R is false, then not R is true. So remember the little squiggle, the tilde, which is I'm not drawing very nicely here, simply means not. Okay, so not R. All right, in the next column, we combine Q and not R. We say Q or not R. So we're looking at the Q column and the not R column. And since remember that V stands for the word or, and so we only need either Q or not R to be true in order to list a truth value of true in this column. So the only time Q or not R is false is when Q and not R are both false. Then we construct a column for P and R. Here, in order for the P and R column to be true, P and R must both be true because the upside down V, remember, means and. All right, then we have some implications. Remember, we always apply the arrow last. So P implies Q or not R. So we're going to be looking at the P column and the Q or not R column. And the only way this premise is false is if P is true and Q or not R is false. So notice that that only happens here. That's the only place where P is true, Q or not R is false. Therefore, P implies Q or not R is false. So again, let me remind you, even down here where P is false, in the bottom part of the table, if P is false, it doesn't matter what the truth value is for Q or not R. We're going to say that P implies Q or not R is true. And then you'll repeat the process for Q implies P and R. Okay. Now, for the conclusion, P implies R, we're only interested in the rows where the premises are true. Okay, so take a look at this would be a critical row. This is a critical row. This is a critical row, and this is a critical row. So we don't need to test P implies R for the other rows because they're not critical. Notice that for every premise, for every row where both premises are true, we have, well, not everyone. We have that row leads to a true conclusion, and these do. However, not this one. This row demonstrates that the argument form that we were looking at, this argument form is not valid. This is not a valid argument form because there is the possibility that the two premises could be true, but the conclusion is false. Now, granted, there are lots of cases where it would actually work out, but since it doesn't work out in all critical rows, then we cannot say that it is a valid argument form. An argument form consisting of two premises and a conclusion is called a syllogism. The first and second premises are called the major premise and the minor premise, respectively. And the most famous form of syllogism is called a modus ponens. This is where you have an if-then statement, and then you assert that P is true. Well, if P is true, then Q is true. So if P implies Q and P is true, then our conclusion is Q. So that's called modus ponens. Here is another example of this, or a specific example of this form. It says if the sum of the digits of this number is divisible by 6, then the number is divisible by 3. Okay, so there's your if then. Okay. The second statement, the sum of the digits is divisible by 6. Our conclusion, the number is also divisible by 3. Modus tollens is another argument form where we begin with an if then statement, if P then Q, and then we assert that not Q. Well, if not Q, then certainly not P, because we know that the contrapositive of a statement is always has the same truth value, or it's always logically equivalent to the original statement. So if P implies Q, then we know that not Q implies not P. Remember, that's called the contrapositive. So if we assert that this is true and this is true, then our conclusion is not P. And that's called modus tollens. And here's an example. It says, if the sum of the digits of the number is divisible by 6, then the number is divisible by 3. The sum of the digits is not divisible by 3. So here we have P implies Q, and now we're saying not Q. Our conclusion is that the number is not divisible by 6. So that would be our not P. You can use modus ponens or modus tollens to fill in the blanks of the following arguments so that they become valid inferences. So first it says, if there are more pigeons than there are pigeonholes, then at least 2 pigeons roost in the same hole. There are more pigeons than there are pigeonholes. So we have our P implies Q statement, and then we assert that P is true. So our conclusion by modus ponens is that Q must be true. Okay, so we would say there are at least 2 pigeons roost in the same hole. And that would be here by modus ponens. In the next example, it says, if the number is divisible by 6, then it is divisible by 3. So there's our P implies Q. The number is not divisible by 3. Now remember, being divisible by 3 is the Q part, not the P part. So we're saying not Q. So by the contrapositive or modus tollens, we can say that not P. So the number is not divisible by 6. And that's modus tollens. All right, let's talk about a rule of inference. It's a form of argument that is valid. Thus, modus ponens and modus tollens are both rules of inference. We have some additional examples of rules of inference that are frequently used in deductive reasoning or logic. So here are some forms that are valid. So let's say we know P is true. Then we can conclude that P or Q is true. So think about this. We know P is true. We can conclude that P or Q is true. Makes sense, right? Because for P or Q to be true, only P or Q has to be true, and we already know that P is true. So regardless of if Q is true, P or Q must be true. And then the same thing, the other statement just says if Q is true, then certainly P or Q is true for the same reason. As an example, suppose you're given the job of counting the upperclassmen at your school. You ask what class Anton is in and are told he is a junior. So here's your reason. Anton is a junior. That means that Anton is a junior or a senior. So knowing that upperclassman means junior or senior, you can conclude that Anton is an upperclassman. All right, let's take a look at this. Suppose you know that P and Q are both true. P and Q. This is true. Then you can conclude that P is true. Seems obvious, right? If P and Q are true, you can also conclude that Q is true. So this allows you to take an and statement and sort of dismiss extraneous information that you don't need for your argument. So if P and Q are both true, but you really only need to proceed with P in your argument, then you can do so based on this argument form. So, for instance, suppose you're looking for a person who knows graph algorithms to work with you on a project. You discover that Anna knows both numerical analysis and graph algorithms. So, here's how you reason. Anna knows numerical analysis and Anna knows graph algorithms. So you can conclude Anna knows graph algorithms and proceed because the fact that she knows numerical analysis, while impressive, is not pertinent to the job at hand. All right, here are some awesome other valid argument forms. So we have P or Q. We know that P or Q is true. And we know that not Q is true. Well, if not Q is true, then that means Q is false. And if P or Q is true, then we can conclude that P must be the one that is true. And the second argument is really the same thing or very similar. Let's say P or Q is true. And you know that not P is true, meaning that P is not true. You must conclude that Q has to be true. Again, I encourage you to pause, think about these forms, process them, let them find their way into your brain until it can rest there in some type of understanding as to what they are saying. So these last arguments that we've discussed seem almost like common sense, but we certainly don't want to make assumptions. So these argument forms say that when you have only two possibilities and you can rule out one, the other must be the case. So here's a specific example. Suppose you know that for a particular number x, x minus 3 equals 0, or x plus 2 equals 0. If you also know that x is not negative, then x is certainly not equal to negative 2. So x plus 2 can't be 0. So by elimination, you conclude that x minus 3 must equal 0. All right, transitivity is another useful argument form that is valid. So we have two premises, P implies Q and Q implies R. We can conclude that P implies R. So if I write it out in a string, P implies Q, Q implies R. Therefore, this transitivity allows us to kind of bypass the middleman. Here's an example. If n is divisible by 18, then n is divisible by 9. If n is divisible by 9, then the sum of the digits of n is divisible by 9. And so we can so this P leads to this Q, and this Q leads to this R. And so we can really kind of eliminate this Q statement and just say P implies R. If n is divisible by 18, then the sum of the digits of n is divisible by 9. It's called transitivity. Here we have P or Q as one of our premises, and also P implies R and Q implies R. We can conclude R. Okay? So It often happens that you know one thing or another is true. And if you can show that in either case a certain conclusion follows, then this conclusion also must be true. For instance, suppose you know that x is a particular non zero real number that is not zero. The trichotomy property of the real numbers says that any real number is either positive or negative or zero. So if you know that it is not zero, then you can conclude that it is either negative or positive. All right, so by elimination, you know that x is positive or x is negative, and you can deduce that x squared is greater than zero by arguing as follows. X is positive or x is negative. If x is positive, then x squared is greater than zero. If x is negative, then x squared is greater than zero. Therefore, since in both cases we've shown that x squared is greater than zero, we can conclude that x squared is greater than zero. The rules of valid inference are used constantly in problem solving. Uh, we don't always stop to name exactly what we're doing or the logical forms, but we do these all the time, not only in mathematics, but just in life itself. Now, along with valid arguments, of course, we have to address the fact that there are some fallacies in argument. These are errors in reasoning. And again, watch a commercial, look at an ad, watch the news, listen to a politician. You'll see errors in reasoning all the time. So when you have an error in reasoning, this is an invalid argument, and that's produced by a fallacy. Fallacies are, we have some common ones listed here. Three common fallacies are using ambiguous premises. Using an ambiguous premise might be something like um, saying, "Oh, she's pretty." Well, that's pretty ambiguous. Exactly what does that mean? Uh, how can we define this? And so, ambiguity is one common fallacy, and of course, treating them as if they were unambiguous. Also, circular reasoning, assuming what is to be proved without having derived it from a premise, and also jumping to a conclusion without adequate grounds. So, we're going to discuss two other fallacies called the converse error and the inverse error, which give rise to arguments that superficially resemble those that are valid by modus ponens and modus tollens, but are not in fact valid. We can show that an argument is invalid by constructing a truth table for the argument form and finding at least one critical row in which all the premises are true but the conclusion is false. Another way is to find an argument of the same form with true premises and a false conclusion. For an argument to be valid, remember this: every argument of the same form whose premises are all true must have a true conclusion, every single one. It follows that for an argument to be invalid, this is important, for it to be invalid, it means that there is an argument of that form whose premises are all true and whose conclusion is false. So we only need to find one argument of that form where the premises are true and the conclusion is false to say that it is an invalid argument. All right, so let's show that the following argument is invalid. If Zeke is a cheater, then Zeke sits in the back row. So Zeke being a cheater, we're going to let that represent P. Zeke sits in the back row is statement Q. Zeke sits in the back row. Now remember, that's Q. Now, if you look back at all of our argument forms that we have discussed so far that are valid, you will not find this. We cannot say that Q, because Q, then P happens. All right. This is like saying if P implies Q, then Q implies P. This is the converse, and that is not necessarily true. Okay. Perhaps Zeke sits in the back row because he's shy. Okay. Met doesn't necessarily. So cheaters sit in the back row, but perhaps shy people sit in the back row also. Now, again, you will find that people make these errors in arguments all the time. All right, here's an inverse error. If these two vertices are adjacent, then they do not have the same color. These two vertices are not adjacent, then these two vertices do have the same color. All right, so here's what we have. We have P is the two vertices are adjacent. Q is they do not have the same color. These two vertices are not adjacent. That is not P. So then we have concluded not Q. So here's the form. P implies Q. That's true. Not P is true. So we conclude not Q. We cannot make that assumption. So if P implies Q, we cannot say that not P implies not Q. That's an inverse. This is the inverse of the statement. And we learned earlier that the inverse of a statement is not logically equivalent to the original statement. Now, this is where it starts getting a little confusing. We can have a valid argument with a false premise and a false conclusion. So the argument can be of the correct form, but the premise and conclusion are not true. So the argument below is valid by modus ponens, but its major premise is false, and so is its conclusion. So let's just look at this. It says Canada is north of the United States. We'll let that be P. If Canada is north of the United States, then the temperatures in Canada never rise above freezing. So that's our if then statement. P is Canada is north of the United States. Q is temperatures in Canada never rise above freezing. The next statement says Canada is north of the United States. That's P. We conclude Q, temperatures in Canada never rise above freezing. So we have P implies Q as a premise. We have P, and our conclusion is Q. This form of argument is a valid form called modus ponens. Okay, that is a valid form of an argument. However, the statement is actually not true. If Canada is north of the United States, then temperatures in Canada never rise above freezing. Well, I've been to Canada in the summer, and it's very much above freezing. So that is a false statement. Temperatures in Canada never rise above freezing is false. Even though this is a valid argument form, the premise and the first premise, at least, is false, and the conclusion is false. So having a valid argument form is not really saying anything about the statements themselves. It's just about the form of the argument. The argument below is invalid by the converse error, but it actually has a true conclusion. So this is just the opposite of the previous example. Even though the statements are true, the argument form is not valid. All right. So it says if New York is a big city, then New York has tall buildings. New York has tall buildings. So we conclude that New York is a big city. So again, this is the converse error. P implies Q does not mean that Q implies P necessarily. So this is not a valid argument form. However, it is certainly true that New York is a big city. So having a valid argument form, again, does not necessarily speak to the truth value of the actual statements themselves. So we've talked about valid arguments. We've talked about invalid arguments that have some type of fallacy. We say an argument is sound if it is valid and all its premises are true. Okay? So that's what we're really hoping for is we want a sound argument. Not only is the form of the argument valid, but all the premises are also true. Okay, so if that is not the case, then we say it is an unsound argument. All right, this video has a lot of information. Let's talk about contradictions and valid arguments. If you can show that the supposition that statement P is false leads logically to a contradiction, then you can conclude that P is true. So if you can show that not P is false, then you can conclude that P is true. So sometimes it's easier to show that something is false rather than to show something is true. And so we will use contradictions many times simply to make an argument easier. Let me give you an example. Suppose you walked into a room of people and someone said, "Everyone here is wearing tennis shoes." Well, if there is a bunch of people in the room, it might be time consuming to walk around and check the footwear of everyone in the room. So if you can find one person who is not wearing tennis shoes, then you can show that that original statement is false. All right, show that the following argument form is valid. So not P leads to a contradiction, therefore P. So we can actually use a truth table to show this. So we have P, there are only two options for P. P is either true or false. And of course, not P takes on the opposite truth values. Notice, look at this column with the contradiction. A contradiction is always false. So not P implies C. We would be looking here and here. We would be looking for, is there a place where not P is true and the contradiction is false? And that's the only time this would be false. Now, if we want to check the conclusion, remember we want a critical row. The critical row is where the premises are true. So we're only interested in that first row where the premises are true. And since the conclusion is also true, P, then we see we have a valid argument form.